And it's finally time, my boys, for... Oh, didn't see you there, I just came from downstairs. Need to get some chalk for this video right here. And it's finally time, my boys, for...
Papa Flammy's Random BOI.
Oh yeah. Thank you guys so much for 15,000 subscribers. I have no idea how I reached this point. Like a few months ago I was at like, I don't know, 5,000 subs, and then I did Papa Flammy's Integral week, and now we are back with a little special week, and we are going to start it off with some really nice integral. It might not look really spicy on first sight, but it's really an awesome one. And I want to present to you a way of solving this bad boy right here without any really special tricks, just algebraically in the end. So let's go ahead and get started. That one is annoying me, I'm placing it here. And at first I would like to introduce a little phase shift. If you don't know what I'm talking about, link to all the corresponding videos will be in the description. So at first, let sum u be equal to pi over 2 minus x. What would happen if we would differentiate both sides? So that means that du is nothing but minus dx. We can plug all the new information in. And don't forget, after doing substitution, this integral I is still our integral Bois I. So we end up with an integral. Now going from, if we plug a 0 into this x, we end up with pi over 2 as the lower bound. And if we plug a pi over 2 into this x, we end up with pi over 2 minus pi over 2, which is just 0. So upper bound is 0, and now we end up with sine squared of. If we bring this x to the other side and then subtract u on both sides, we end up with pi over 2 minus u. Same thing happens to the arguments down here. So we have the sine of pi over 2 minus u plus the cosine of pi over 2 minus u. And now we have a minus du right here. So multiplying both sides by minus 1, because it's not equal to 0, we end up with minus du. And the great thing now is we can distribute this minus into this integral to change the upper and lower bounds. So that's amazing, because we end up with the same upper and lower bounds here. And also there's a nice little property regarding this phase shift right here. I haven't derived this yet. I'm going to at some point of time. Sine of pi over 2 minus u is going to become cosine of u, and cosine of pi over 2 minus u is going to become sine of u. Keep this in mind, we are going to plug all the new information in. So all in all, we are going to end up with the integral going from 0 to pi over 2 of sine becomes cosine. So we have the cosine squared of u over sine of u, so that's this right here, plus the cosine of u, and now we have a du. And just like I said before, substitution is an equivalent process, so this thing right here is still I. And it doesn't matter what you call this variable right here. It can be this beamer I see up there in the corner, or it can be this chalkboard, your mother, your dog. It doesn't really matter. We are just going to call this thing right here x once again. So that means we can add I and I together to get 2i in total. So we end up with 2i now being equal to, well, we are adding this with this one together. We have the same upper and lower bounds, so using the linearity of the integral, we end up with one integral going from 0 to pi over 2. And also, we have the same denominator, so we can add those two together. So over sine of x plus cosine of x. And also we are having sine squared plus cosine squared in the numerator. Cosine squared of x plus sine squared of x. dx in that case. There's a nice little property regarding this numerator. Cosine squared plus sine squared is going to evaluate to a 1, so that's nice. This is going to cancel out, and also we can multiply both sides of this equation by 1/2, not equal to 0, so we can do this to get a final expression for our I. So that also means, equivalently speaking, that I is now nothing but the half integral going from 0 to pi over 2 of, now we are having dx over cosine of x plus sine of x. And just like I said in the beginning, we want to make this integral I into something algebraically. We can do this by exploiting some nice trigonometric properties. We're going to introduce a new substitution. So let sum t be equal to the tangent of x over 2. It might not seem obvious at all how this weird substitution with some half angle is going to help in the least bit, but it's going to help really badly. And we're going to do this on the next blackboard. So we are now having a new trigonometric BOI. And the first step is to differentiate both sides right here, because we just introduced the substitution. So that also means, that's itching, that dt is nothing but. So we have an argument right here, 1/2 times x. So we need to drag the 1/2 to the front. That's what happens when you differentiate. And also tangent differentiated is just the secant squared of the argument. So secant squared of x over 2 dx. But that's not good, because we have a secant squared of x over 2 right here. We're going to deal with this in a minute. At first, I want to take a look at cosine and sine right here, because we need to express it with respect to t, somehow. That's not quite easy, not quite obvious, but you will see in a second how it works. So at first, I would like to take a look at, it doesn't quite matter, let's take a look at sine of x. So the bad thing at first is that we have a sine of x, but we introduce the substitution using an argument of x over 2. So why not transform this right here into 2 times x over 2? So that's something that holds. So this is equal to sine of 2 times x over 2. But this is not even half bad, because we can use the double angle formula for the sine and later for the cosine on this thing right here and see what we get. So at first we end up with 2 times the sine of x over 2 and then times the cosine of x over 2. So we've got that out of the way. We are having everything with respect to x over 2 now. That's not bad, that's nice. But now we need to express it with respect to the tangent right here, so that we can express it as some function of t. How can we do that? Well, we are pretty close to having a tangent here, because we have a sine. If we would just have a 1 over cosine of x over 2, I'm mixing all those arguments and stuff up, English is hard, then we would indeed end up with a tangent. How can we get that? Well, we can multiply by 1 this whole thing. But what is a 1 exactly? Well, this is just a cosine of x over 2 over cosine of x over 2. Distributing it into something, we end up with the sine of x over 2 over cosine of x over 2. This indeed is the tangent of x over 2. And also we have a cosine squared now. I hope you could follow where this came from. Take a piece of paper, write it out, and you will see that the cosine and one of the cosines cancel out, and we end up with the same expression. Nice and fine. But now we have another problem. We have this cosine squared right here. That's not very good. We also want to transform it into a tangent. Cosine squared, what is that? I hope you agree with me that cosine squared is nothing but cosine squared over 1. And you guys know what a 1 is. A 1 is nothing but, just like discussed before, a cosine squared of x over 2 plus a sine squared of x over 2. Once again, we would like to get an expression for tangent, so why not factor out a cosine squared right here on this whole denominator, so that we get sine squared over cosine squared. So if we do that, let's transform it that way. We end up with 1 plus sine squared over cosine squared of x over 2. That's quite a mess right here. I don't want to write everything out. It would take ages. That means that this factor and this factor is indeed going to cancel out. We end up with 1 over this expression. And let me write everything out now. All in all, we end up with that sine of x is nothing but 2 times the tangent of x over 2 over, and this is 1 over 1 plus tangent squared. So this is 1 plus tangent squared of x over 2. I hope you could follow everything I said. And that's great, because we have expressed everything with respect to the tangent. And now we know what the tangent is. Tangent of x over 2 is nothing but t. So all in all, we end up with 2 times t over 1 plus t squared. That's amazing. Awesome. And now let's deal with the cosine part right here. Cosine of x. Just like before, same reasoning, we want to transform it into something that includes x over 2. So that's cosine of 2 times x over 2. There's a double angle formula for the cosine. It says that we have the cosine squared of x over 2 minus the sine squared of x over 2. And once again, it would be nice to get an expression for tangent. That means why not factor out a cosine squared on this whole expression? So we end up with, now we have the cosine squared of x over 2, and then 1 minus, and sine squared over cosine squared is just the tangent squared of x over 2. Whew. But we know what this is right here. This is just 1 over 1 plus tangent squared. So all in all, we end up with 1 minus tangent squared of x over 2 over, and now we are having 1 plus tangent squared of x over 2. This is sliding up on its own. It's cursed. Okay, and this right here we can indeed express with respect to t, so we end up with 1 minus t squared over 1 plus t squared. So we are done with the most part. Let's just deal with this differentiated thing right here. With this differential boy, we are having a secant squared. So let's put it here. dt is nothing but 1/2. But what is secant squared? Secant squared is 1 over cosine squared. So we have 1 over cosine squared x over 2 dx. But we know what cosine squared is. Cosine squared is just this weird expression, 1 over 1 plus tangent squared. And taking the reciprocal by having this inside this fraction, we end up with 1/2 times 1 plus tangent squared of x over 2. Okay, and we can express this with respect to t. This is now 1 plus t squared over 2 dx. Now we can multiply both sides by 2 over 1 plus t squared, not equal to 0. And then we have an expression for dx, which we can plug in. And then we are done with the hardest part. Let's move on. I forgot one little thing, a little fact. So we've introduced the substitution, but we haven't talked about the upper and lower bounds. So what would happen if we plug a 0 into the x value? We have the tangent of 0. This evaluates to 0, so that was easy. And if we plug in a pi over 2, that's the tangent of pi over 4. You can use a calculator, calculate it by hand, it doesn't matter. We end up with a 1. And that's quite nice, because now we have an integral going from 0 to 1, and we are going to solve an algebraic expression. It's easy to solve in the end with those nice values. Let's move on. Something you might notice, this 1/2 and this 2 is going to cancel out to 1. And also you could factor out in the denominator this 1 over 1 plus t squared, and that's going to cancel out with the 1 in the numerator. So that's nice. We've simplified that quite nicely. Now we end up with the integral going from 0 to 1 of dt over, and let's put it that way, minus t squared plus 1 plus 2t. Oh no, plus 2t plus 1. That's even better. Okay. We've got a problem now. Solving something like this isn't too easy. Because, how would we integrate that? We might want to factor it and then use some techniques, for example, partial fraction decomposition, to make 2 integrals out of it. But that for later. But we have another problem. So if we would like to factor that, we have a negative sign in front of the squared term. That's not good. We would end up with something complex, I times something. We don't exactly want that. So why not factor out a -1, for example? Maybe that does work. So we factor out a -1. That means we turn around all the signs. Still not good. Same problem. So this 1 squared right here has a negative sign in front. We would like to turn this around a little bit. How can we do that? How can we change the sign? Maybe we are doing some algebraic manipulation. For example, we could add a 0 down here. So adding a 1 and subtracting a 1. Right again. It wouldn't change anything. I hope you agree with me. And that's nice. So we have a positive 1 right here. And why not bring this -1 and -1 together to have a -2, for example. Okay, nice. And now we have something we had desired. And now we can distribute this minus into this 2 right here in this -2 and bring it to the outside and see what we get. So we have manipulated that quite nicely. Now we have the integral going from 0 to 1 of dt over, let's put it that way, 2, that's this one right here, minus, and now we have t squared minus 2t plus 1. And that right here is something we can actually factor. That's awesome, because this right here is going to evaluate to integral 0 to 1 dt over, and now we have 2 minus And what is that? Well, this is exactly t minus 1, but the whole thing squared. And if you take a closer look, we actually have the difference of two squares, because a 2 is nothing but square root of 2, but squared. And now we have the difference of two squares, and we can actually evaluate that. Integral 0 to 1 of dt over. And now we have the first part. So this is square root of 2 of minus. And then we have to turn around the signs for the first part, so minus t plus 1, and then times square root of 2. And now we are having a positive sign, so everything stays as it is, positive 1, negative 1, positive t. And now we have factored that. And just like announced, we have to use partial fraction decomposition on that to work with it further. But it's not half bad this time, it's quite easy. So, partial fraction decomposition, I hope you know how this works. So we are now going to make partial fraction decomposition on this stuff right here. Square root of 2 minus t plus 1 and times square root of 2 plus t minus 1. It's going to be really fast, no worries. So the first factor, this has a degree of 1, this has a degree of 1, so we are nice and fine just having a's and b's up here as constant. So square root of 2 minus t plus 1, that's the first one, plus b over square root of 2 plus t minus 1. Now we can multiply both sides with this big denominator under the condition that it's not equal to 0. We are going to assume that. So that also means that 1 is now nothing but. So we have a times this, because this, and that is going to cancel out. So we have square root of 2 times a plus a times t minus a. And also we have to multiply this by that, this, and that is going to cancel out. So multiplying b by this first term. So plus square root of 2 times b. And also we have negative bt and then positive b. The degree of the polynomial on the left side is 0. That means we also need to have a degree of 0 on this side. So that means we need to get rid of all the terms that include t. So that means at minus bt needs to be 0 in this case. We can cancel out the t's right here, not equal to 0. That means a is equal to b. That's awesome. So if we plug this in, we got rid of that. And also a is equal to b, so this is going to change to an a. This is going to be an a. And well, no, this hasn't cancelled out. This has cancelled out. And this and that is also going to cancel out because we have minus a plus a. So that's nice. And now we end up with 1 is now equal to 2 times square root of 2 times a. We can divide both sides by 2 times square root of 2, not equal to 0. That means a is nothing but 1 over 2 times square root of 2, which is also b. And that's it with the partial fraction decomposition. Let's plug everything in. Now let's hurry things up. This boy is already taking ages. It's just how it is. I told you, it's going to be a pretty nice way. And nice things need some time to flourish. So what we can do, I have plugged everything in and I have used linearity of the integral to break this up. So we could factor out this 1 over 2 square root of 2 as a common factor of both integrals. So that's nice. And I would like to introduce 2 little substitutions. So let's, I don't care, v be equal to this denominator right here, square root of 2 minus t plus 1. We would end up with dv being just minus dt. Those are constants. And also, why not let w be equal to the other denominator, square root of 2 plus t minus 1. That also means that dw is nothing but dt. We can plug all the information in, just like I said, factoring out this factor right here. We end up with, okay, our new upper and lower bounds. If we plug a 0 into here, well, this is going to cancel out, so v is going to be a square root of 2 plus 1, and if we plug a 1 into here, minus 1 and 1 cancels out, so it's going to square root of 2. That's nice, and also now we have just minus dv over v, so we have this negative sign right here, and same procedure here, plus integral going from, if we plug a 0 into here, we end up with square root of 2 minus 1, and also if we plug a 1 into here, we end up with square root of 2. So same upper bound as here. That's quite nice. It's going to cancel out in the end. Woo! Okay, great. And now we just have dw over w. And integrating those is extremely easy. So we end up with 1 over 2 times square root of 2. And now we are having the natural log of v going from square root of 2 plus 1 to square root of 2. And also it's negative, don't forget your negative sign, or you can just change around the upper and lower bounds, it doesn't quite matter. And then positive natural log of w going from square root of 2 minus 1 to square root of 2. Those have inverted signs, they are going to cancel out. This negative sign in the second part of the integration going to become a positive sign, and we have a negative sign here. So plugging everything in, we end up with 1 over 2 times square root of 2. And now we are going to end up with the natural log of square root of 2 plus 1. That's strictly positive, so we can get rid of the absolute values. And then negative natural log of square root of 2 minus 1. Strictly positive, that's something like 1.4 minus 1 is something 0.4. That's awesome. And we are basically done. We can make this a bit nicer, for example, so we can use the natural log property to get 1 over 2 times square root of 2 natural log of square root of 2 plus 1 over square root of 2 minus 1. And we can multiply this by a 1. What is a 1? Well, a 1 is nothing but square root of 2 plus 1 over square root of 2 plus 1. So this is just the conjugate right here. And this right here is the difference of two squares. After that, so we end up with 1 over 2 times square root of 2 natural log of. This is going to be square root of 2 squared. So this is a 2 minus 1 in the end, so that's a 1. So we are just ending up with square root of 2 plus 1, but the whole thing squared. But what is that squared? Well, let's just calculate it real quick. This is 1 over 2 times square root of 2 natural log of. We are going to end up with a 2 plus 1 in the end, so that's a 3, and then 2 times square root of 2 plus 2 times square root of 2. And now we are done. Awesome. So that's the solution to this nice little integral, and I hope you enjoyed the first episode of Papa Flammy's Random Week. If you did enjoy this video, please like and subscribe and recommend me if you like. If you want to support me a bit more, link to my Patreon is in the description. I'm doing all the stuff for free, so I would highly appreciate some support from you guys. Don't forget to activate your notification bell to receive all notifications regarding my channel. And up until the next video, have a random, flammable, fabulous, whatsoever day. See ya.
Papa Flammy's Random OIAAAAA ha he Papa Flammy's Random OIAAAAA ha he Papa Flammy's Random OIAAAAA ha he Papa Flammy's Random OIAAAAA